Hi, in today's video, we'll be giving a short introduction and just an intuitive sense of what is the beta distribution in probability theory. So, a beta distribution is just, in layman terms, what it wants to achieve is that it models the distribution on probabilities. So, what does that mean? Well, we'll just talk more and you understand what does this line mean, that it is the probability distribution on probabilities. So first, let's give the PDF, which is a probability density function of the beta distribution, as that is what defines a distribution. So it's x to the power of alpha minus 1 bracket 1 minus x beta minus 1 over the beta function with the parameters alpha and beta. In this case, since the idea that it is the modeling probabilities, the probabilities only can range from 0 to 1, and so the support is from 0 to 1. And this beta function, you can expand them out into these gamma functions. More can be found online, so we'll skip this part, but this is the PDF for the probability distribution for a beta function distribution. And how does this really intuitively model the probabilities? Well, it has a close relation to binomial. As you can see, the parameter here x is to the power of alpha minus 1 bracket 1 minus x to the power of beta minus 1. If you remove the constant here, which is also called the normalizing constant, it is proportionate to this numerator. And what do we see when we write a binomial PDF? The probability of a success being x is just the total number, choose x, times probability to the power of x bracket 1 minus probability of success to the power of n minus x. And you can see this term looks awfully similar to this term over here. And so while the binomial models the number of a success, we can take that the beta models the probability of success. So we can say, like, it can model questions such as how likely is this president going to win the election based on the votes right now, the given votes. So what is the probability of having this as success probability? So it means that you can interpret the alpha minus 1 as the number of success and the beta minus 1 as the number of failures. So this is the close relation it has to a binomial, and it gives you an intuitive sense of how does the beta distribution models probabilities. Now, more intuition for the beta distribution. Let's say you have a coin. You have 10 coins, and each of them has a probability of landing heads from 0 to 1. So 0, 0.1, 0.2, 0.3, all the way to 1. Now you plot the graph of having a beta distribution of having 2 success, 8 failures, 8 success, 2 failures, 5 success, 5 failures. And in this case, the success will just mean the chance of getting a head. If you work out the binomial distribution for this part, you will realize that 0.8 will give you the highest probability of getting 8 successes. And this can be described with the beta distribution, where after normalization, and you plot out the beta distribution for having 8 success and 2 failures, it achieves the peak at 0.8. Similarly, symmetry will detect that for 2 success, 8 failures, it will be 0.2. And you can think that if you have an equal number of success and equal number of failures, then it achieves the highest probability of having that outcome when it is 0.5. And this is more intuition of how it plots models the distribution of probabilities. For even more interesting facts, it is also related to uniform distribution, as the uniform distribution is a specific case of the beta distribution. Now take that the beta distribution is 1, 1. Then you know that alpha minus 1 is the number of success and beta minus 1 is the number of failures. And so, when your beta 1, 1, it means that you can have 0 number of success, 0 number of failures. And so, without knowing anything, you will guess that the probability is evenly distributed throughout the support. And so, this will equate to uniform 0, 1. But this is just an intuitive, and the mathematical proof can be found online. So, after doing all this intuitive thinking of what the beta distribution is and how you can use it to find the probability of your success rate, we want to know how is it useful and what can it be used for. Well, one application is that it is proven to be the conjugate prior for the Belloni, the binomial, the negative binomial, the geometric distribution. So you can see that it is the conjugate prior to distributions that deal with successors. And being a conjugate prior, it makes computation easier when you want to compute very large posterior probabilities for many iterative times. As let's take that the prior probability is following a beta with parameters alpha and beta, and that the number of success follows a binomial with n number of trials, and this p being this probability distribution from the beta distribution chance of success. Then now, knowing how many successes, let's say k, your probability will be updated due to Bayes formula, and this will be the new posterior distribution, which also follows a beta distribution with alpha plus k number of success, comma, beta plus the number of failures, which is just n minus k. So you can see the posterior can be derived from the prior easily. And so this makes computation easier, as if you want the next posterior, you just calculate this again and add on and add on. Let's see this in code. So in terms of our code, we'll code them in Python, and first we'll import all these. So NumPy will import beta distribution, t, norm, everything, and then we'll just run it. We'll import some additional libraries to help with the plotting of the graph. And let's say you have a probability of 0.8 at the start. Then you create some random occurrences, and then when you run it through a binomial distribution with probability p and the number equals to n, this will be the number of hits occurring, and this is the number of tails occurring. And you just see that the number of hits is 83 and the number of tails is 17. So now we can start. So before knowing the experiment, you don't know anything about the heads and tails. And so the prior heads and prior tails, you can take it to be equal, to be 1, 1. And then you update it based on the number of heads you get. You update the beta based on the number of tails you have. And then you create a random variable which follows a beta distribution, and now the new alpha and beta, or A and B. You run the plot, and you see that the peak is somewhere around 0.8. Because this value up here is not exactly 80 to 20, this will be what it shows now that you updated the values. And you can just use a loop to run it multiple times if you need to calculate a posterior. This can be very useful for optimization, and other forms of approximations, which you can read more online, as this is just a short introduction on what is the beta distribution and how you can code a one-time use to update the posterior. If you do not know that it is the conjugate pair, you need to do a bit more complications, such as multiplying with the likelihood function, and that will complicate your code. And so with just the knowing that it is the conjugate pair, it allows us to update the posterior easily by just adding. As you can see, this is the usefulness and how beta distribution models the probability distribution of successes. And so I've come to the end of the video, and I've hoped you've liked it. Please feel free to like, share and subscribe, and comment on any questions you have down below. Thank you.